Hi, everybody. We are the cloud-based, wait for it, gapless sea surface temperature, or SST product mentored by Zhenjia. And our project focused on an SST time series for its wide application across oceanographic disciplines. And many applications of SST fall under the ocean state forecasting, including contributors to biological productivity, weather, and extreme events, which require high spatial and temporal resolution to improve accuracy. Here we have two views of the GOES geostationary operational environmental satellites, and a view of how SST nicely shows the mesoscale structure of the Gulf Stream.
Right, so now that you guys have heard about some of the applications of satellite sea surface temperature data, I'm going to be talking about a couple of the challenges that exist, especially when working with high resolution satellite sea surface temperature data, some of which we've tried to address this week. So the first of these is accessing and working with very large data sets, as can be expected with high resolution satellite sea surface temperature products, which are very large files which take a long time to load in. So we started off this week with a bunch of NetCDF data sets. And as you can see here, loading in about 1 day with hourly resolution took about 3 minutes. And then to subset and plot it, it took about 44 seconds. We then decided to convert a subset of this data to ZAR, just to show how much faster it is to import and use this data. And again, so this time we were importing a month of hourly data, and it only took 5.5-ish seconds to ingest that, and then another 1.4 second to plot. So that's kind of how we've addressed one of these challenges. And second of all, if you want to hit next, Kylene. We've also tried the other big problem with high resolution satellite data is the difficulty that cloud cover creates. And in a kind of lower resolution product, it's easy and you can kind of average this out over a longer time period to get a relatively gap-free product. But when you're trying to create a really high resolution product, this can be a big issue. So I'm now going to hand over to Patrick to talk to you a bit more about that.
Right. So our goal with the interpolation here, spatiotemporal interpolation, was to produce a 6-hourly gap-free global sea surface temperature product. And to create this gap-free product in the study area you can see here, and just for reference, that top left bit of white, that's like the Delmarva Peninsula, Chesapeake area, so just for some spatial reference. But we use PyKrieg, which uses kriging for spatiotemporal interpolation. On the bottom left here, you can see the variogram plotted against spatiotemporal lag. So as you would expect, variance rises as you get further and further away from the point of interest. And in this small study area, we don't even really go to a full decorrelation. This is just a day of data and a couple 100 kilometers. But you can imagine if we had a larger spatial range, a larger temporal extent, that would sort of flatten out to some decorrelation. So on the right there, you see our sort of final product after we create this kriging, which is based on this variogram model on the left. And we're able to interpolate out in a way that looks relatively believable. You do see some sort of the smoothing effects of this interpolation, but it's certainly a usable product without crazy outliers. So the next steps for us are to better balance the influence of space and time on this model. Our current version didn't actually have proper decorrelation lengths specifying a temporal window or a spatial range. We certainly don't want it to fill something 10 days away and 100 kilometers away, so deciding what's realistic. And after improving the model itself, our goal is to scale to a full hemisphere and then the globe. We were consistently running up against memory limits with the Oceanhackweek AWS nodes, pretty consistent crashing. Solving this matrix inversion for this interpolation is pretty compute intensive. For example, on a 1,000 by 1,000 grid with 24 time step, it was like 100 gigs of RAM. So just, not feasible on this. And you can do it in sort of a moving window approach, which is what we ended up doing, but it takes a lot longer. So luckily, the problem is pretty easily parallelizable. So scaling with X-Ray, Dask, and Kubernetes in the cloud is the next move. And then we'll have some really exciting data to explore the ocean's variability. So thanks, everybody. Thanks to our mentor, Shell, all the organizers, and the presenters.